All right. Still in Article 2.6, I want to mention a couple of special cases. We're dealing with resultants, if you recall. In our last video, we dealt with the general scenario of non-concurrent forces, and we located a resultant for F1, F2, and F3, the way it was shown here, by using what we called the principle of moments. And the principle of moments was really just an extension of Varignon's theorem to take the moment produced by each one of these forces around point O to form a single force couple description, and then to simplify from that single force couple description to a single force at a specific spot. So we've already done the most difficult and the most general scenario, which is the non-concurrent forces. Two other scenarios that show up are when we have concurrent forces. So if we have a system of concurrent forces, as you see here, F1 and F2, and the lines of action for these two forces pass through this common point A, then what you would find is that the sum of the moments about A would be equal to 0. We wouldn't have any moments around point A, and so your resultant line of action for the body is really nothing more than the parallelogram rule of addition for F1 and F2 to get R, and that is where it's located, and that is the actual resultant. So all you really have is that R is the sum of the forces. You don't actually have a moment because there's no moment around here at point A. Now, you could compute the moment around any other point that you wanted, but again, you wouldn't find any new information because this would give you everything you need. So R would be the simplification of F1 and F2 for this body. There is another system that you can have, and that is of parallel forces. All right, so, and when I get here to parallel forces, let me do something first. So we have three forces, F1 and F2 and F3, and what we find, this is a very special case. This, might happen, once or twice, but it's not very common, but it is a special case. So we have F1 and F2, and by intersection point, we find that they have their resultant, with parallelogram rule of addition, acts at this point, and then that resultant winds up being equal and opposite, in this case, to this third force F3. So they're parallel. Now, for this one, where we've shown them as equal and opposite, note that the sum of the forces would be 0 for this. So this actually has no net resultant force. But just because there's no net resultant force does not mean that there is a net or no net resultant moment, because the F1 plus F2 producing minus F3, and then F3 separated by a moment arm here, would have a resultant moment, M, that's equal to F3 times D. So you can still have a resultant moment, even if there's no resultant force. Now, if all the forces wound up being parallel, then one nice thing you would do is just put your coordinate axes in the direction of the parallel forces, and then that would make it very easy to add them up vectorially. But this one is not only parallel, but it has this notion of parallelism, but also has a 0 resultant force. So just a special scenario. Again, it's not a common thing that you'd run into a lot, but it could occur. All right, that's it as far as resultants are concerned, and we'll work a bunch of examples so you get comfortable with it. All right.